The most likely is that you're looking to learn about PLCs and you landed on this video. The other possibility is that you already work with PLCs, and because the Micro 800 controller showed up in your venue or your location, you now have to learn how to work with those using Connected Components Workbench. Either way, we're going to sort this all out before we get too far in to make sure that this is where you want to be in your learning process. This particular set of videos is aimed at Connected Components Workbench specifically for programming the Micro 800 controllers. And this is the manual that you see in front of you. Part 1, there's 2 parts to the manual. It comes as a set. Originally, when it was printed, because it's 350 pages, it was too cumbersome. So I split it into 2 documents, separately spiral bound. What you see here is part 1, but there is a part 2. So what is a PLC? We're going to give you everyone the benefit of the doubt here. And if you already know what a PLC is, you can fast forward or just skip ahead. What is a PLC? Programmable Logic Controller. Now, I'm not going to go back and go through all the history of a PLC. But basically, a PLC is a device that will process the state of input field devices against a set of instructions provided by the designer to operate output field devices. So in the processor, you have RAM, random access memory, you have machine-specific coded instructions, and you have data. The machine-specific coded instructions and data must be written and downloaded into the RAM of the processor. Otherwise, it's not going to control anything. So you're looking at a basic PLC right here. Let's start much simpler. The processor is the computer. The input and output electronics that you saw in the previous diagram, that is simply an interface between field devices and the processor. So let's consider just the processor. You could call that a computer that has a CPU and memory. It's also going to have other chips in the set to handle I/O, to handle communications, etc. But let's keep it simple. You have a processor, which means you have computing power, and then you have memory to work with. A processor without memory is absolutely totally useless because everything takes place in the memory. First of all, you have to have a point of access to the memory so you can download your program. If you have no communication ports into the processor, you can't do anything with that processor. Now I showed 2 communication ports. And let's just say that the communication control, that's a chip or a set of chips that facilitates a connection between external devices and random access memory. Communications port. Typically it's channel 0 and channel 1. Channel 0 is typically RS-232, and channel 1 these days is most often Ethernet, TCP/IP, or Ethernet IP. That's a story for another day. Now we have a processor with memory, and we have some way to access it. Inside of the memory, when we download something, remember that memory is just 130,000 or so individual bits, electronic devices that can represent 2 states, on, off, 0 or 1. And there's nothing different between one bit and another out of the 130-some thousand bits, or 8,192 16-bit words. It's just memory. It's like a section of land, and there's nothing on that land except it's flat clay and it's covered with grass and weeds. 1 square foot is the same as another. Once you download something via the communication ports, and that could be from RS Logix, Connected Components Workbench, any programming software, whatever controller you have, you're downloading into memory a virtual image, so to speak, of your process. In this case, the terminology here, System 0, System 1, Ladder 2, then S2, B3, and so on. This is the image of a controller that falls into the RS Logix 500 platform. Now, you came here for Connected Components Workbench, but remember, it's either because you're starting new in your career with Connected Components Workbench, or you are already using RS Logix, and now you're going to learn how to use Connected Components Workbench. So this is a good starting point for people that have RS Logix background. If you don't have the RS Logix background, don't worry about it. System 0 and System 1, those are system files that you cannot access. They're for certain functions. Ladder 2 or File 2 is where your program is at. Now, you can have more than one ladder file, but let's just stick to LAD 2. That's where your program, your instructions. All the instructions in this list of instructions reads from or writes to other locations in memory. In this case, I'm only showing you S2, which is the status of the processor, B3, T4, C5, R6, N7, and F8. If you're not familiar with RS Logix, B implies that these 16-bit integers are going to be used at the bit level. T is for timer. Those are 3-word elements of an array of timer data types. That's where we'll just say your timers are. C for counters, R for control words. So T4, C5, R6, each one of those elements is made up of 3 integers. N7, the N implies integer, and so that's an array of 16-bit integers. But you can use the bits. You can use the individual bits in N7 or B3 exactly the same. And then F8, floating point. So keep in mind, if you're going to write a program reads the state of something and writes the wanted state somewhere else. So ladder 2, every instruction there is going to read something from one of those data files, S2 through F8, and then write to the same data files. Now there is something missing simply because we haven't shown it yet. So you could download a program into this controller, this processor, and it could run the program, but it would be limited to reading and writing to those 7 files on the right of ladder 2. However, that doesn't control anything externally. So that means we need I/O, inputs and outputs. So first up, we'll throw an input module. Now, this input module, it's a 16-bit input module, which means that the state, on-off state of those 16 inputs will occupy, eventually, a 16-bit word in the memory in the processor. And those states will get there by way of a backplane. Now, a backplane, and they are rapidly disappearing. Control Logix still has a solid rack or chassis with a backplane. But in a nutshell, the backplane, and we'll simplify it down to 16 conductors, kind of like a ribbon cable, but traces on a circuit board that run the full length of a chassis that can accept multiple modules slid in and plugged into those 16 common conductors. And the state of those 16 inputs then would be transferred across that backplane and stored somewhere in memory. In this case, it's going to be stored in the I1 data file. So I and 1, they look kind of alike, and I think that's how they ended up with making data file 1 for inputs, because an I looks like a 1 or a 1 looks like an I. That means that this processor with its I/O chipset will activate that module, and that will cause the state of those inputs to be felt on the backplane. The processor will then read those states and store them in I1:X. I have an X because there can be many slots, and so you would have a word for each slot. We're going to keep it simple though. Let's add some outputs. Now we have inputs coming in, and the state of those 16 inputs now only show 8 or so, or 10. But you notice it goes 9, 10, 11, and then ... 15, 0 through 15. So those are stored in I1:X. X could be any number representing the slot. In this case, it would be slot 0, so it would be I1:0. Now keep in mind that not all PLCs have this identical nomenclature, but they all work exactly the same in this aspect. So now we add an output module, and the output module actually receives data from memory, from a word or area of memory that begins with an O, because it looks like a 0, or 0 looks like an O. So that means that whatever states you want those outputs to be in, I see an amber light, a contact relay coil, a solenoid, 3 motors, a red indicator, and another solenoid. So we have 8 outputs there. Well, actually we have 9, because I have another solenoid down on output 15. But the point is that green box O0:X is a 16-bit integer, and at some time those 16 bits will get transferred out on that same backplane that the input module is on, but to an output module, and it tells those outputs what state that you want them to be in. Now, of course, none of this happens unless you have a program downloaded into Ladder 2. Now, when you put the processor in the run mode, it's going to read the state of those inputs, period. But it's not going to update any outputs unless there's something to update. Well, actually, I take that back, it does. But because you didn't change the state of the outputs, it's just always going to send zeros out there. And regardless of the state of the inputs are all going to be off. Backing up a little bit, the processor chipset, the I/O chips, they go get the input image. In other words, they buy another set of conductors that go out there on that backplane. So I said to use 16 wires. Well, really there's more than that. There's a common, and there's power, so that's 18. And then there's another separate little bus of 4 or 5 conductors. It's called the control bus. And it activates those slots or those I/O modules one at a time. So when it comes time to get the input image, the processor activates slot 0. That puts the state of those 16 bits on the backplane, and the processor, because it knows what slot it activated, it puts those 16, the input image, into I1:X. So it stores it. Then it executes the ladder diagram, and when it executes the ladder diagram, it's going to read any of those 9 data table areas in the program. You can read an output bit. You can read an input bit, an S2 bit, B3, 2. You can read any of that. So your instructions, ladder logic instructions, they're going to read words or bits from that data file over there, and then if the rung is true, it's going to change something to 1. If it's false, it's going to change something to 0, and so on and so on. So it goes through, it reads not just the input image, but it can read anywhere from that data table, and it's going to create an output image. So when you get all the way through the ladder program, the results, you could say, when it comes to the output field devices, that's the output image. And so at the end of the program scan, remember we collected the inputs up, input image, we ran the program, that created an output image, and then we send the output image out over the backplane to that module. And that's pretty much as complicated as you can make it. Then it does it all over again. It reads the inputs, stores them in I1:X, and remember X can be 0, 1, 2, 3, 4, 5, it could be anything, depends on how many modules you got. Then it executes the program, ladder 2, creating the output image, then the output image is sent out on the backplane to the output module, and then goes right back and does the input image again. Now there is a little sliver of time in there when it does housekeeping tasks and checks on certain parameters, does communications. because you can alter the state of these data table values directly from channel 0 and channel 1. So basically there's 4 phases, and we'll say it does the background or communication housekeeping task, then it gets the input image, reads the program, creates an output image, sends it out on the backplane, and then goes and repeats that again. Burn this picture into your head. Now the only thing that's going to vary with other hardware and other programming software is instead of seeing system 0, system 1, ladder 2, and then O0 colon something, S2, B3, the variables and the program files may have a different look to them, but I guarantee you what's going on here is going on in every single PLC out there. Some of the more advanced systems that they call PACs, Programmable Automation Controller, they're a little bit more complex. They're a little bit more efficient in the way they handle things, but still, you write a program that reads from the data table and writes to the data table, and those results then are felt in the output image to control your machine. If you have more than one, in this case more than one, 2, I show slot 0 for both. You can ignore that. It really doesn't matter what slots they're in. And a lot of what you call a PLC, it's really a controller. The difference between a processor and a controller is all PLCs have a processor and they have I/O interface. And you're looking at 2 I/O interfaces here, one for input, one for output. So this whole thing together is a controller. A controller has a processor. It also has input and output electronics. That's a controller. Not all PLCs have it all built into one plastic box. For instance, all control logics and most compact logics have a separate processor, and then you plug in the I/O modules. So there's a processor and then individual I/O modules. All of the Micro800, which is where we're headed, they are all controllers. There are no separate processors. Every single Micro800, whether it's the 810 all the way up to the 870, they are controllers. They have a processor and embedded I/O built right into the little plastic housing. Another look, a little bit more complex consideration, but the same thing. We're looking at memory now, and we've got program files, and you can have multiple program files. Now this is from RS Logix 500, okay, not from Connected Components Workbench. And if you've never worked with RS Logix, then just consider the process that you're looking at here, that you have a ladder diagram that, as a matter of fact, if you look at the rung in there, ladder 2 main routine, that first instruction is a true if on. So if input 0.0/0 is on, then that instruction is true. If input 0.0/3 is off, then that's true. So the rung is true, and it writes a 1 to output 0.0/0. So see, real world conditions, inputs read, and then the result write to the output word, and that goes out and causes real world actions. All the rest of the data files are internal, like status of the processor, B3 bits, T4 timers, C5 counters, control integers, floating point, etc. Now I show this expanded out because with RS Logix 500, you can have all the way up to ladder 255. So ladder 2 you get whether you like it or not. So in ladder 2, if you want to have ladder 3, ladder 4, and you don't have to have 5 to have 9 to have 17. You could have ladder 2 and ladder 255 if that flips your switch. So it just gives you the ability to organize your ladder logic, your code, into different subroutines to make it easier to handle. If you look in the main routine, ladder 2, you have JSR instructions that jump to 3, 9, 4, and 255. Now this is RS Logix 500. not Connected Components Workbench. Let's look at Connected Components Workbench, so to speak. So we're making a transition from the diagram that we already looked at. And instead of System 0, System 1, we have System and I/O. We have it clumped into one called Global Variables. Now this is more closely related to RSLogix 5000 than 500. So this is actually a more effective use of the memory than in RSLogix 500 supported processors. So this is leaning more now towards the Micro800. So you have what's called global variables, and you don't have a ladder 2. If you remember, you had ladder 2, but then in ladder 2 you had to have jump to subroutine instructions to get to these other areas. In the Micro800 family, you have global variables, which is I/O, and then you have the ability to create multiple programs. In RSLogix 500 supported stuff, you could only have one program. And in that one program, you could have multiple routines. In Micro800 land, instead of one program, you could have multiple programs, and each program has its own isolated, encapsulated set of variables. Now, in case you're wondering what a variable was, I'll jump back here, and output :x, input :x, S2, T4, N7, etc. Those are all variables. They are memory locations defined with specific data types for you to use in your program. With 500 products, RSLogix 500, all the variables were predefined. You could expand, but you couldn't create any pointers or variable names outside of what you see right here. With the 800 family, you have a little bit more latitude. Yes, there's global variables, and the I/O variables are fixed. You can't change the way they look. But all of your local variables, you can name them anything you want. And remember that a variable is a pointer that's defined as a certain data type that points to an actual literal numerical memory location in an array, a memory array. You'll never know the actual numerical location. You'll create a variable with a data type, define it as a data type, like a counter, timer, Boolean, etc. And when you download, it's compiled and it converts all the stuff that you have, we'll say English, Spanish, whatever language you use, into actual numerical memory locations. You'll never see those, but they're there. So your variables are pointers that point to an actual memory location. So we have the same thing here though. Across the backplane, we collect up the input image and we store it in the global variables. Then we execute the program, changing the state of both global variables if they're outputs and local variables. And each program can read any of the global variables and only the local variables of their program. So that means program 2, it can read and write to and from global variables and to and from the local variables in program 2. But it cannot see and or touch anything in program 1 or program 3. And then of course the output image is sent out. In this case there is no real backplane because the Micro800s, especially the 810, you cannot expand it. Now the 820, 830, 850, and 870, you can expand the I/O. So theoretically it does have a backplane even though it's kind of encapsulated in the plastic box, and you can see where the modules insert on the front. Now, a quick review of what we offer, and the reason I'm doing this is because I want to make sure that you're right where you need to be in your learning process, because there's so much stuff on the website that people get confused. All this information right here, disc 1, 2, and 3, those are lectures. They're just straight up technical lectures on PLCs, etc. And then the disc set that you see down below, the first 4 discs anyway, not that last one that says information, but the first 4 are lab discussions from one of the manuals. Now I'm going to pause here and I'm going to go to the website to show you how to access these lectures. When you get on the website, this is what you're going to see. In the area that we're primarily interested in is virtual classrooms. Now just so you know what, all the tabs are up there. Home is where you're at. Start here. If you can pick, well, you should read this first. And then there's some categories here so you can identify maybe where you might want to start in your learning process. We're not interested in that right now. We'll go to virtual classrooms, and under virtual classrooms you can see a variety of subjects. And electricity magnetism, that's virtual classroom room 101, basic electricity magnetism. If I click on that room, it takes me to a list of lectures in that room. In this case, there's 3. And if you open up one of these, we'll just open up one, it will actually take you to YouTube and start running
Welcome to part
the
2
video. And it's going to cover all the basics
It could be a septic
of electricity magnetism. When you close out, when you close YouTube, it's going to put you right back in the classroom and you can go to the next lecture. If you are rock solid with your electricity magnetism, don't waste your time watching any of this. But if it's been a while, it wouldn't hurt you to peruse through this, because a basic understanding of electricity magnetism is a good thing. Back to virtual classrooms. Next up is programmable logic controllers. And in here, you've got an introduction to programmable logic controllers. That's primarily where you're going to start. And you have a list of lectures here. You see in red I have a connection for a hex conversion under binary number systems. But you can start watching these videos, and they start right at the beginning with
whenever the switch is as generic as possible, to say that to prevent the...
So you can see it starts right at the beginning talking about relays, and it gets into some very important characteristics of relays that maybe you didn't consider before, and that is that these contacts represented by symbols, normally closed and normally open, a normally closed contact queries that coil to see if it's on or off. And this contact is electrically true if the coil is de-energized. This is electrically true conductivity, if this is energized. So there's a lot that you really need to make sure that you understand under all of these. Now, you don't have to go through all of these, but it's a good idea to watch these. The rest of it, don't worry about it. So that's how you get to the virtual classrooms. And here we have the lab project discussions. If you're using the 1000, 1100 manual, if you're using the 1400 manual, and so forth. So I'm going to drop back out of this and get back to the slides. Depending on where you're at in your learning process, this is the most basic lab project manual. Now, those lectures that I showed you, they in a way support everything that we have, because they're somewhat generic, but all PLCs work enough alike that those lectures, not the lab discussions, they go along with specific manuals, like this manual. So this manual was originally in 3 volumes, then converted into 1. It's been updated, and it says with MicroLogix 1000. However, the disk that comes with this, that software will program the 1000 or the 1100. Now this manual's a little different in that it is exhaustive of all 70 some instructions that the 1000 supported. The other manuals aren't exhaustive. They're more a lot of practical applications and programming challenges. So this manual is a little bit different, and it's worth going through if you're an absolute beginner, and it's also the least expensive way to get started. Then we have, it's very similar, but it's not exhaustive in the instructions. There's much more programming and understanding of different styles of programming, but it was accomplished with a Micrologix 1400. Now, the manual that you just saw, or this one, can be used with any Select 500 in any Micrologix. The only thing that you have to be aware of is the I/O assignments might look slightly different, but everything else is going to be identical. And as the lab discussions are available in the virtual classrooms for that black and silver manual, they are also all there, at least for right now, for the black and orange manual that uses the Micrologix 1400. So either one of these two is a good starting place if you're just learning PLCs. Jumping right into RSLogix 5000 I don't think is a good idea. And of course, if you're here for Connected Components Workbench with the Micro800, hang in there, we'll get there. Then for RSLogix 5000, there's for the beginner, a Basics, and then there's a Basics Plus. Again, there was way too much content to put into one spiral bound document, so we broke it into two. And each of these has their own lab lecture discussion video sets. For the beginner, they are in optical disc form, but we have recently switched over to jump drives, thumb drives, memory sticks. So you see a little bit shape different of the label. That's going to be on a memory stick. Eventually everything will be on memory sticks. These two manuals occupy well over 500 pages, close to 600. So we boiled that down. We took most of the content and put it into one manual called the Collegiate Edition. In other words, we removed some of the more basic concepts like number lines for working with comparison instructions. If you have computer science and you're good with math, you could go right to this lab project manual and not use that set right behind it. Now, the video disc sets for the blue and the green one, they're basically, you're going to find most of those lab projects in the red manual. So there's not a separate video disc set for RS5000 Logix Engine, the Collegiate Edition. The lab discussions are going to be on these same two discs. And actually, these were our first RSLogix 5000 manuals. These are written for people that are already well accomplished with RSLogix 5 and 500 and just wanted to make the jump to 5000. We have that broken up into two volumes, and that includes projects with all four of the languages, a motion lab, add-on instructions, lots of user-defined data types, etc. And each of these has their own set of lab lecture discussions. So now let's get back to CCW, Connected Components Workbench. So at this point you should be able to decide, I'm on the right path, I want to work with CCW, or wait a minute, I might want to start with the Micrologix. Now, if you're new into the PLC field and you landed on CCW with a Micro800 because it looked cheap, you're going to spend more time, a lot more time, learning PLCs with CCW and the Micro800 than you will just paying the money for the not free software for MicroStarter that programs the Micrologix 1400. You can buy a used Micrologix 1400 L32BXB. You can buy it on eBay for roughly $200. Build yourself a little push button box with lights wired up and have at it with the orange and black manual. That would be my advice. But if you need to learn CCW, you're in the right spot. Just hang on for the next part of the lecture. This is the manual we're working with. I'm going to start in the beginning of this manual and start going through it and discussing what we had you do in the manual. Now, if you don't have the manual and you want to stop, order one, and use the manual or not, it doesn't matter. You can keep listening and watching, and you can learn without the manual to a certain point, and then it's going to become more difficult. because I do not go over everything that's in the manual in the video. That would be really a waste of time. So I will go through some things that are in the manual, but I'm going to elaborate, which that's typically what you get in a classroom setting, is you have a textbook or a project manual, but the instructor elaborates on many things that are not in the manual and does not discuss everything that's in the manual because we're assuming that you read it. So let's get on with this. Although there are videos all over the internet of how to download and install Connected Components Workbench, I'm going to breeze through the current format of doing that as of late 2018. It constantly changes. Rev levels change, feature packs change, a lot changes. The way that I would always do it, and have done it, is I go to Google and I type in CCW. Now that might get me there, but I could also put in AB, for Allen Bradley, and then hit enter. Well, there you go. Right off the bat. All over the place. You could click on either one of those first two. I'll just pick the first one because it's the first one up. Now, it just so happens that I am permanently logged in to Rockwell Automation. I didn't get the login. In other words, it didn't come up and say I need to log in or sign in. If that's what you get, then you have to create an account. And it's free. Username and a password. There's just no way around that. And you're going to be using stuff off of their site off and on for years. So you might as well just go ahead and create the account, and then you'll get to this page. And on this page, you'll see some marketing information, and you'll see a short, if you want to call it discussion or bulleted point on the current software version level, which happens to be 11, and the very first feature pack that ever came out, and it came out for version 11. And you can go down here, there's some videos that you could watch. I don't know how good they are. Typically, Rockwell makes their videos more marketing and selling features oriented and not practical. But there's always a little information that you can glean. Look down through your system requirements. If you've got an Apple laptop or computer, you can load Windows on it. Personally, I like Windows 7 Pro. I've never used 8. I owned a laptop, or actually it was a tower with Windows 8 for one day. I hated it. Took it back and bought another Windows 7 Pro. Now I do have a number of Windows 10 computers that I use in the classes that I teach, and all of my big screen TVs have towers or laptops of some sort, and they're Windows 10. So I am forcing myself to adapt to 64-bit Windows 10. So read through this to make sure you're ready to go. And now, here's an important thing. You've got Standard and Developer. Standard is free. And if you're just getting started, by all means, download version 11 software Standard and have at it. However, if you're serious, then I would be considering the Developer, because there are certain features that you're not going to have to use with the Standard. But guarantee you, the Standard is good enough to get started and learn what you need to learn. If you mouse over here, you see that's a link, and you can download. Now, you can't download the Developer without paying for it. And that you have to buy from your local Allen Bradley distributor. So if you do a search on Allen Bradley distributor in your area, call, ask for technical sales, and when they answer, tell them that you want to purchase the Developer Edition of Connected Components Workbench, and they'll set you up and give you a price. I bought it. I don't remember how expensive it was, but it didn't even give me pause for an instant. And then from there, you're going to download something. And once it's downloaded, then you're going to install it, and then you're going to open the software. Now I'm going to open the software, and I will probably pause once the splash screen comes up, so you don't have to sit here and watch that splash screen open up into the full software. And after a long wait, I even went and made myself another cup of coffee while I was waiting for this to open. I'm sure it didn't take that long, but it took a while. So don't get impatient. This is what popped up. Now, I'm going to pull this out so it fills up my space. A lot of what you see here would not appear when you open your software the first time. All of this recent stuff here, none of this is going to show up. Now, I could have went in and kind of emptied this out to give it more of a fresh start look, but why bother? Because before long, you're going to have things down there for recent. And of course, you know what recent is, right? The most recent thing that I worked on was video recording 1. I don't even know what that was. It was something that I was trying out as an approach to doing the CCW. But nonetheless, you get the idea. And before that, July 8th, 2018, PowerFlex 525. This software, Connected Components Workbench, does much, much more than just programs for the Micro800 family. It does a bunch of other stuff. We'll point it out a little bit, but we're not going to go off into all the other things that it can do. What we really want to get to is the Micro800. So right now there is no project open. And I'm going to assume that for you, you don't have any recent, so there is no open existing, right? You don't have an existing. There is Discover, but we're going to leave that alone. We're just going to go to New. And I'll make this Project 1 simply because whatever was created before Project 1, I don't care about it. So I'm going to say Create. Okay, it doesn't like that. It's a name already used, so it's complaining. So I'll change it a little bit. Okay, it liked that. Project 01. I already had right down here. See, I had Project 1 already. So what's interesting is it doesn't follow the normal Windows format of coming up and saying, do you want to overwrite an existing file? It just doesn't let you create it. Now that may change. By the time you're watching this video, that could have changed. So what it pops up and says, okay, you want to create a project, you need to add a device. Now you can add devices over here. See the little plus sign? But it's still going to bring up this dialog here. And I have the choice between controllers, drive, safety, and graphic terminals. So I'll start at the bottom and I could do panel view 800s or I could do panel view component. For motor control, I can do soft starters, the SMC Flex or the 50 standard. There's some safety devices, safety relays and light curtains. In other words, you can add those to your project and configure them. Now, I don't use these bottom three. I might use the graphic terminal eventually, but typically I do something. When I'm doing engineering, I typically am using Factory Talk View ME. I've not had cause to do a graphic terminal in Connected Components Workbench. Let's go to drives. Okay, and they add more to this list ever so often. Well, the PowerFlex 520 and specifically the 525, really nice little drive that supports Ethernet IP, and you can buy them new on the internet for between $350 and $500, and you can buy the 115 volt version, and you can buy a 3-phase 230 volt motor from Oriental Motor for about $125. It's a little 125th horsepower, a little bit bigger round than a beer can and not quite as long, and you can actually build yourself a little PowerFlex 525 variable frequency drive training station. As a matter of fact, if you go back to my website and go to Live Classroom and View Hardware, you scroll down, you'll see how we take and combine a PowerFlex 525, the 115 volt single phase input version, with that little 3-phase motor. However, today we're not interested in drives, we're only interested in controllers. And right now, currently, there's Micro 810, 820, 830, 850, and 870. The Micro 810 is a world unto itself. and it comes in 4 flavors. And these 4 flavors have to do with the I/O interfaces to the field devices, AC, DC, etc. I typically always use the QBB because it gives me the most capability when you get up into the more powerful controllers. I'm not going to select one yet. So 820s, 3 flavors, 830. And actually an 820 QBB is a good choice. However, it does not have a conventional connector for the RS-232. It does have Ethernet. In the 830, it has the conventional RS-232, but it doesn't have the Ethernet. I would avoid the 830. My personal preference would be the 820 with the HMI that costs another couple $100, because that gives you the USB connector and it gives you Ethernet. Otherwise, I would jump to the 850 or 870, and of course they're more expensive. Well, to right this instant, we're going to pick the LC10. I select it, and you can drop down this list and look, but if you just acquired yours, it's going to be whatever the latest version is, most likely. We're not going to cover flashing firmware, and I happen to know that my 810, I have 3 of these that I work with. I have an 810, an 820 with the HMI, and then I have an 870. I have a broad range of these controllers to work with in developing the manual and the lab projects. Most of them, if not all of them, you can do with the LC10. But I will say this, with the LC10 you're not going to get online programming. I mean, you can change it from run to auto, from run and program mode. You can change the mode, but you can't edit the code online. The 820 and up you can, but the LC10 you can't. So if you've not purchased your controller yet, I would seriously consider jumping from the less than $100 LC10 up to a 20 with the HMI on it. When you add the HMI onto the 20, that gives you the standard USB port to plug into, and USB is cool. I like it much better than the standard RS-232 interface. Also notice that there's a plastic cover here on the LC10. There's a plastic cover here and there's one right here. This LC10 for $85, $90, whatever it is, does not have an LCD display, and this is not a conventional communications connector. You have to spend another $35, $40 for a USB adapter module that you plug in here that you can plug your USB cable in. So for all practical purposes, you might as well say that an LC10 is going to cost you roughly $140 by the time you get the USB adapter. And if you want the little LCD screen, that's another $40, $50. So you're going to be closer to $200 for an LC10 with a little screen and with the USB port. But we're going to go ahead and pick that. See, it gives you the details right here. So I'm going to select it. When I say add to project, what it's going to do, it's going to take the class of objects 2080-LC10-12QBB. That is a class of data objects, and it's going to create an instance of it and add it to my project. And if you're not familiar with information object modeling, information objects, class of objects, instances, it won't kill you to go to YouTube or the net and search a little bit, read, and as soon as you do, you go, oh yeah, this is nothing. I understand this. Dog, that's a class of objects. German Shepherd, that's an instance of a class of objects. You get it. Now I've created an instance of the information object Micro810, QBB in this case. And you can see that's all right here. I can, under controller, this is the general information, and I wish I could collapse some of this because I don't need to see this, but I want you to see what's down here. Under memory, there's nothing for you to see until you actually build something. See? Memory usage is only updated after a build. And then you've got startup interrupts, real-time clock. And under real-time clock, you could set the date and time based on the date and time of your computer, your laptop. Okay? You can go to Embedded I/O and it shows you what you have. And so you've got some analog inputs, but no analog output. You have 8 inputs. Okay, so here you have 0, 1, 2, 3, 4, 5, 6, 7. And here you can set your filter. It's like a debounce filter. It filters out noise. In other words, it ignores anything that's less than 8 milliseconds, any change in state. If it doesn't stay for at least 8 milliseconds, 16 milliseconds, 32, etc., it ignores it. It's just a noise filter. Well, these 8 inputs, the first 4 share the electrical interface with possible analog inputs. So you don't have 8 inputs and 4 outputs plus 4 analog inputs. You got 8 inputs. 4 of those could be used as analog. Okay, so that's all you get down here under this. Now, LCD module, I do have one. Okay, so just for grins, I'll attach it. Oh, there it is. So all that I did was took a instance of the class of objects, Micro810, and I modified it to include a sub instance of the type of object LCD module. And you can do some things with that LCD module. Actually, if you're going to use the 810, you might as well spend the $40 and get the cute little LCD module, but you definitely have to have the USB connector adapter that plugs in here. Okay, so I've created this instance of an LC10 QBB. Now, if I go to programs, notice up here, I got start page. You recognize that, right? That's where we started. And now we've got this new page, Micro810. I'm going to go to programs and double click. Nothing happens because there aren't any programs. I'm going to go to global variables and double click. And there is something to happen. And that is these are the global variables that come with an instance of a Micro810. So these are the variables that include all the I/O. See right here? You've got digital output 0, 1, 2, and 3. You've got digital input 0, 1, 2, 3, 4, 5, 6, 7. And then you've got analog in. So remember that these 4 right here share the same electronics as these 4 right here. You can't have them be both. Now the rest of these are system variables. We're not going to discuss them. I just wanted to give you a quick look-see what the global variables were. There's not going to be any user-defined function blocks, and there are no data types because actually, there are some data types. I'll bring this into view here. Structures, but there's no instances of these. Okay, these are data types. Totally ignore them. And then defined words, there are none because you haven't defined any yet. So there are no arrays, there are structures, and there are no defined words. So this is a bare naked Micro810 project. So there's really nothing here. Now I could close this Micro810 global variables here, or I can just click on another tab. I'm going to go here, right click, and add a ladder diagram program file. There were no program files before. Now see, you got program 1. And you can name that anything you want. You can name it Monkey Doodles. Okay? Now here's what I want to point out that I pointed out earlier in the lecture. Here are the global variables. There's your I/O. Okay? And here is your first program and the local variables, of which there aren't any. So this set of variables right here can only be accessed from program 1. So program 1 can read and write to local variables and global variables. If we create a second program, program 2, now we have 3 tag databases. We've got global variables and they're accessible to Program 1 and Program 2. And we've got local variables, but inside of Program 1. So Program 1 can work with these or the global variables. Program 2 can work with its local variables and the global variables. But Program 2 cannot see or touch these local variables part of Program 1 and vice versa. Program 1 cannot access or do anything with these local variables. Okay, that's a Micro 810. And I think I'm going to, this lecture's gotten long enough, so I think I'm going to start another one and talk about other microcontrollers, Micro 800 controllers beyond the 810, just in case you're starting there. We're going to continue this discussion in the next video. The first one got longer than I expected. It's up to an hour. That's way too long. We'll go to another separate video and we'll continue talking about the Micro 800 hardware before we get into the more specifics of programming.